So we are in the eastern Alaska Range now. This is the Delta River. It's a large braided river that's going to flow down the northern side of the range. Up above us here, all these red and gray colors, this is called Rainbow Ridge. And this is basement strata of the Wrangellia terrane. So we're going to look at the Skoli Group, including the Station Creek Formation, and this will be the roots of the Wrangellia terrane.
Wow.
What we're talking about is basically the remnants of an old oceanic arc called the Skoli arc. So these rocks, this is called the Skoli Group, and we're in the Station Creek Formation. And so these are mostly volcaniclastic sedimentary strata. So it's a little tough to see in this outcrop, but you can see some layering or bedding that's dipping about maybe 50 degrees in here.
Yes.
These from afar often look, like volcanic rocks, but up close, they're largely volcaniclastic in this particular outcrop. So, these are sediments that are made of volcanic material being generated in the arc. But another feature that's pretty interesting in this outcrop is these darker brown dikes and sills. So above Mike's head there's this darker, more dull brown, cuts at about a 40-degree angle up to the left.
Yeah.
And these are basaltic in composition, and these were most likely feeding the Nikolai flood basalts that we're going to see later this afternoon.
So can we get an age on the Skoli and an age on the Nikolai shooting through?
Yeah, the Skoli up here in this part of Alaska is latest Pennsylvanian into early Permian, so around 300 million years old.
Thank you.
And then the flood basalts and any dikes or sills that are part of feeding that, those are going to be late Triassic, about 230 to 225 million years.
All before Pangea time.
Yep.
Okay. And I'm sorry, since this is just such a stunning view of Rainbow Ridge, does this outcrop down low have anything to do with what's up high?
Yeah, they're generally part of the same package.
Okay.
I haven't been up there to say exactly what the lithologies are, but we have these reds and grays, and throughout the sequence it's going to be mostly volcanic flows and volcaniclastic strata. In parts of the upper part of the arc sequence, it'll also get into carbonates, so there will be some limestone deposited over the arc sequence.
So Ken, we're in central Alaska, and it's possible that this Wrangellia here in central Alaska is continuous all the way down to Ellensburg, Washington.
It's possible it was all once part of a continuous unit, and it's been fragmented by strike-slip faults like we've discussed. But that's what's so really dramatic about this sequence, is that you could go down to Vancouver Island and see the same rocks. And that's what makes these reconstructions along the margin so enticing, that we can start to say, well, it was here, was it continuous, or was it a series of little island arcs that have been separated?
Right.
But that connection to Vancouver Island is a pinning point.
And Wrangellia doesn't stop here. It continues off to western Alaska.
Exactly. And goes into the subsurface somewhere out there. And so it's I would say the largest addition of juvenile crust to western North America that we've had, during the Mesozoic time.
And because we're in a collisional part, we're seeing a third dimension to Wrangellia that we don't often get a chance to see.
Absolutely. And you can see these rocks were tilted. You see how high that ridge goes.
Excellent. So how many of these feeder dikes have been found?
Thousands.
Thousands of these.
That's all this discoloration you're seeing up through there.
Wrangellia basement, even with those pyramids.
Yeah.
And plenty more Nikolai feeder dikes coming up through, presumably.
Yeah. And an interesting thing for the broader Nikolai conversation is that when you get really close to the base of it, including on Vancouver Island, in fact, really well documented there, it's mostly these sills. And, as you can see, Wrangellia basement is not exposed everywhere. We've been driving through all this covered stuff. And When we've been thinking about how much extension could have played a role, in the past it's often been argued that there's not really a lot of true dikes that you would associate with that. I think that's still a question that we could circle back to, because if you have a reason to think about extension in the upper plate like we now do in the late Triassic, that's a question you want to kind of readdress. But as you can see, you can't find it everywhere at all. So.
Calgary, 100 kilometers, there's differences. These guys get wide mark. Good?
Good. Okay.
Yeah, we've come here along the Denali Highway. We'll show you where that is on a map in a second.
Thank you.
Because as we move up through the Wrangellia terrane stratigraphy, we started today down in the basement, which is the Skoli Group related to late Paleozoic arc. And as we move up into this area, out behind the car there is the best place to look. We have a thick section of the Nikolai Formation flood basalts. And
Wonderful.
these are really the defining unit for Wrangellia.
Want to use this map
Yeah.
before we then look more carefully across the way at the Nikolai?
Yep. Okay, so this whole area is underlain by the Wrangellia terrane in Alaska, and as we've discussed, or will discuss, it's more extensive than that, all down through Vancouver Island. Today, we've come up and looked at some exposures of the basement, which were a little bit south of the Denali Fault. So this is Golconda and Glen Allen, the Denali Fault here. We started down in here.
Okay.
Now we've come over, and there's this road called the Denali Highway, which comes over to the central Alaska Range if we were to continue west. And in this area, we have these exposures of the late Triassic flood basalts, and that's what we're looking at from a distance here. So along the Denali Highway, the Amphitheater Mountains are one of two main locations in Alaska where these have been studied. So this is a little more to the west, and then to the southeast of us here down in Wrangell-St. Elias National Park is the other location for Alaska. These are really the first defining features. So you've heard us talking about Davy Jones and some of the early mappers. For them,
Yeah.
the flood basalts of Wrangellia were really the stratigraphic unit that allowed them to connect parts of Wrangellia up here in Alaska and the Yukon down to parts of Wrangellia in Vancouver Island where you've done some filming.
Nice.
And they're a really important unit for understanding the tectonic history, and there's been a couple different ways that different folks throughout the years have interpreted the flood basalts. They're in this area about 3 kilometers thick, in other areas up in Vancouver Island up to about 6 kilometers thick.
Mm-hmm.
And they were initially interpreted as potentially rift related, and with the recognition that they were overlying some older arc crust that we now know is this late Paleozoic arc crust. That arc was extinct well before it had stopped being active well before the flood basalts erupted. And then it started, another interpretation that started to be proposed and tested was, are the flood basalts instead related to a mantle plume? And there was a lot of work done in the 2000s and really nice work by Andrew Green and others that basically did very detailed chemostratigraphy through these rocks. And so basically that means they're looking at the geochemistry, chemical composition of these flood basalts in a really tight sequence in all these different areas, Alaska, the Yukon, down in Vancouver Island. And they interpreted them as the product of a mantle plume.
So they're called Nikolai up here. They're called Karmutsen down Vancouver Island.
Yeah.
Same stuff, same ages.
Yeah.
And there may be a continuation of these flood basalts all the way down to Vancouver Island, or they may have been offset somehow.
Yeah, there's probably some offset of Wrangellia itself. We have a lot of strike slip faults down through southeast Alaska, for example. But you can find them pretty continuously. You can go from here, again, down into the Yukon.
Yeah.
These basalts are on Haida Gwaii and then down into Vancouver Island. And some of the early mappers would even suggest they may have gone further south.
So how about the usefulness of those flood basalts? Is there an argument to use the flood basalts to help us paleogeographically for what's the age again in numbers of these flood basalts, and where does that put Wrangellia?
Yeah, so the dates are about 230 to 225 MA.
Okay.
And the people who've worked on these most closely and most recently would also say that they probably erupted really quickly, like within 2 million years.
Oh, wow.
So that's, a really important aspect of these. And as far as paleogeography, there's a couple different aspects of the flood basalts to think about. So one is that particularly down in Vancouver Island and the Carmoutzen, there's been a lot of paleomagnetic work done. So folks come out and drill the basalts. They're looking at what latitude they would have been at about 230 and where was Wrangellia. And that's pretty consistently placed Wrangellia between about the equator and 20 degrees or so north or south of the equator. A lot of paleomagnetists don't interpret one or the other, but it's in that range.
I mean, come on, we're in central Alaska and these basalts were very close to the equator back then. That's a huge story, it seemed.
Yeah, and I know you've talked a lot about terrane transport, and one thing I think is important with this time period, late Triassic, is to remember that there's a little bit more time left to move terranes than when we're talking about, has Wrangellia and other terranes docked to North America, whether that's, you say we're talking the late Cretaceous and then you want to move things. So there's still, I know that sounds like a lot of distance, but there's still a lot going on and then a lot of history left to unravel now.
Thank you.
The important thing to remember here is that there were sedimentary basins, strata that were built on top of the Nikolai flood basalts. We're not seeing that here. And it's a thick package of about 7 kilometers of sediment that you can see in the Wrangell Mountains overlying these. Jeff Trop in his thesis found a series of tuffs in the uppermost part of that, which were late Cretaceous. It's called the McCall Ridge Formation. Once we realized that we had those, we said, well, maybe we can contribute to this story. And so for part of his thesis, we worked with a guy named John Stamatikos who ran the Paleomag lab at University of Michigan, and we drilled those. And they would suggest that, again, envision 7 kilometers of rock over top of what you're looking at right now. At that time, these rocks were probably down by British Columbia. So you have a Triassic starting point somewhere near the equator. We have a late Cretaceous point somewhere near British Columbia, Washington, and then we end up here. Thanks. So here we're looking at the transition from the eastern Alaska Range into the central Alaska Range. And as you can see, as we've been driving up, we left the Wrangell volcanoes. We don't see any volcanism here. The arc has shut down because the slab is very shallow here. But once it gets over by the Denali Fault, which is defined by these peaks over here, working with the EarthScope data with Gary Pavlis and Terry Pavlis, a project that we have going on right now, what's really beautiful is that we can see the flat slabs turns downward. And right now it's starting to go into the lower mantle. And as it goes into the lower mantle, it starts to double on itself. And so one thing that I've always been interested in is as this thicker crust comes into the flat slab area, is that what's driving this? Or as that slab gets anchored in the mantle, is that the crustal thickening that we're seeing here? And so that's a project that we're working on right now. And so you can see the role of flat slab, crustal thickening, and strike slip along that, how you can build huge mountain belts. And that's the beauty, I think, of taking tomographic data, combining it with surface data. I think that's kind of the power of tectonics the next 10 years. There's all these different people that are working on it. There's people that are working on the surface, but there's this power in that we could never see before, and understanding what the mantle's doing and how do you build this. You don't build this overnight. There's a process involved, and that's what we want to get at.
Mike, we're thinking about going north over this range, going to the Brooks Range. We've got some surface geology from a generation ago. Do we have mantle tomography up there? Is there a flat slab story up there?
Great question. So that is it's a much older collision. So this flat slab subduction here, it's ongoing right now,
Yeah.
somewhere down below us.
Yeah.
But up in the Brooks Range, that collision terminated in the Cretaceous. Okay, so whatever slab was driving it is now deep within the mantle. Now, as your viewers know, you have talked to Karin Siglock quite a bit, and she would claim that they can see that as their Angayuchum slab. Okay, and the way that would have originated is subduction of an ocean basin called the Angayuchum Ocean Basin that pulled Arctic Alaska underneath an arc that we call the Keough Arc. Okay, and so what we've gotten interested in is this is a place where the subduction polarity seems to not be very controversial. So if you take Karin's model further south in the Cordillera, not only do we have a slab in the mantle that we're linking to surface geology, which is a challenging thing to do,
Right.
but you're also invoking a different polarity.
Yes.
Whereas in the Brooks Range, the polarity is fairly well established as south dipping, which is away from the continent, or west dipping in a North American framework.
Everybody seems to be comfortable with that.
Yeah. And so what we're interested in is if we have, I'm going to kill the whiteboard.
He's using a Sharpie on a whiteboard. I love it.
So if we have the Keough Arc, and then somewhere over here, we transition to Arctic Alaska. If we knew when this started, if we could start the clock, when did the Keough Arc start, and we know when Arctic Alaska entered that trench, we could basically predict that there should be X amount of slab.
Yes.
All right, and that's something that we can match with the tomographic data.
Yep.
So I think Karin is fairly comfortable making some predictions about how long that subduction zone would have been active. And then we can go to the surface geology and ask that same question. When did it start? And we think the best way to do that is to find these subduction initiation ophiolites.
Mm-hmm.
And when did it end? And that's something that we can look at in the sedimentary record of the Colville Basin on the North Slope to figure out. It's known.
Yeah.
Because there's oil up there.
Yeah.
But the Keough part is something that I think we have a reasonable sense for when it started, but it would be nice to shore that up.
We got data from the Foreland Basin. We've got Karin's data from down below, but we don't have a date on the ophiolite specifically that might mark the beginning of that subduction.
Yeah, we know when it ends, but we want to know when the clock starts.
Right.
And so I think that could be really nice because unlike all the disagreements that were discussed over your show this winter,
Right.
up here, you don't have to make too big leaps. There's not the polarity and everything happening offshore.
Yes.
The polarity seems to be well established. So can we match this with the tomographic data?
Oh my God. Before the flat slab was understood, what were geologists saying about this range 70 years ago? Or like just as plate tectonics was starting, was there a different idea?
Well, I think when in the 1970s, what, you know, Coney and Jones would say is that you had this big bend in the Alaska continental margin, and terranes were sliding up during the Cretaceous.
The sliding.
And they can hit here, they couldn't get around the bend, so they shortened, and that's what formed all the high topography. And so they were right in one way, but I think their timing was off in another way, and that this modern topography that we see now is really being driven by the Yakutat terrane and the flat slab subduction of this. So the timing, we have a much better feel now for what Mike and, you know, Aaron and Donachie and other people have done. So that's the difference, I think. It's the timing. They were right about the process in one way, but they had, you know, 15 different terranes coming up. And Wrangellia was one of them, like we've talked about just a few minutes ago. But George Plafker realized that it seems a little too young, and then Paul Fitzgerald did the fission track dating on Denali, the massif itself, and said, hey, this all started coming, there was a uplift started at 20, and then at 6 million, there's a big kick. And then we started dating the fault with students like, you know, Trevor Waldine, Way Allen, Sarah Rusky, and I. Jeff Benowitz was a big part of it. And all of a sudden, it doesn't look like these strike slip faults are Cretaceous. It looks like they're Cenozoic. So you start putting these various pieces together, and then the thermochron data. So this was a new tool, as you might know, where we could actually look at cooling of the Earth's surface. That's really changed the way that we look at all origins in the world. And we add that element to it, and they say, hey, at 30 million years, things are moving up. And so all of a sudden, you have to start questioning the older model.
Yes. Beautifully done. Purdue Geology. Tectonics.
Just for them. I want to take some pictures. Photography for me.